The internet was never designed with identity or trust built in. When two systems exchange data, the network simply carries the traffic. It doesn't guarantee who is sending it, who is receiving it, or whether anything was altered in transit. That gap creates the perfect opportunity for a man-in-the-middle attacker. Someone sitting between you and the service you think you're using can quietly listen, change data, or even impersonate one side to the other. So before we can talk about PKI or certificates, we need to answer three basic questions. How do I keep my data private while it's in transit? How do I prove that I am really me? And how do I know the other side is who they claim to be? Everything in PKI ultimately exists to turn this fundamentally untrusted network into something we can safely build secure systems on top of. When we talk about digital trust, we're really solving those same three problems at the same time. Who are you? Can anyone else read this? And has anything changed on the way? Authentication answers the identity question. Is this really the user, device, or service it claims to be? That's how we prevent impersonation and account takeover. Confidentiality is about secrecy. Even if someone is listening on the network, encryption ensures they only see unintelligible data, not passwords, messages, or business records. Integrity ensures that what was sent is exactly what was received. If an attacker alters a transaction, a configuration, or a software update in transit, integrity checks detect that tampering. PKE exists to give us systematic, scalable ways to provide all three: authentication, confidentiality, and integrity across an untrusted internet. Before we get to PKI and public keys, we need to look at where the problem starts: relying on a single shared secret key. In symmetric cryptography, the same key is used to encrypt and decrypt. It's extremely fast and ideal for large amounts of data. Modern algorithms like AES are designed for this. The real trouble is everything around the math. First, key distribution. If two people need a shared secret, how do they exchange that key securely before they can talk securely? If someone intercepts the key once, they can read everything. Second, scalability. In a group, every pair of people needs its own unique secret key. For 100 people, that explodes into thousands of different keys to create, share, and rotate. Managing that securely is almost impossible at enterprise scale. And third, there's no built-in identity. Possession of the key lets you encrypt and decrypt, but it doesn't prove who actually sent a message. Anyone with the key can pretend to be anyone else. These three issues, distribution, scale, and lack of authentication, are why we eventually moved beyond a single shared key model, and why PKI becomes necessary. Asymmetric cryptography is built on a simple but revolutionary idea. Instead of one secret key, we use a matched pair of keys. One key is public, and one key is private. Your public key is like your bank account number or your email address. You can give it to anyone, post it anywhere, and systems can freely use it to encrypt data for you, or to verify your digital signatures. Your private key is the opposite. It must remain absolutely secret. It's more sensitive than a password, because anyone who gets it can pretend to be you, or read information meant only for you. The magic is in the relationship between the two. Anything encrypted with the public key can only be decrypted with the corresponding private key, and vice versa. That means we can safely share the public key over insecure networks, without ever exposing the private key. This is how modern systems finally solved the key distribution problem that limited traditional symmetric cryptography. Asymmetric key pairs give us two big powers: confidentiality and authentication. For confidentiality, imagine Alice wants to send a secret to Bob. She doesn't need Bob's password or any shared secret. She just uses Bob's public key to encrypt the message. Once it's encrypted, it's useless to everyone except Bob. Only Bob's private key can decrypt and recover the original content. Anyone is allowed to encrypt to Bob, but only Bob can read it. For authentication, we flip the direction. Now Alice wants to prove a document really came from her and hasn't been altered. She uses her private key to create a digital signature over that document. Because her public key is widely known, anyone can verify that signature. If the verification succeeds, they learn two things at once. The document was produced by whoever controls Alice's private key, and the content hasn't been changed since it was signed. PKI builds on these two behaviors. Encrypt with the recipient's public key to keep data confidential, and sign with your own private key to prove identity and integrity. So far, public-private keys give us confidentiality and digital signatures. But there's still a big missing piece. How do you know a public key really belongs to the person it claims to represent? Imagine Alice has a legitimate public key, but an attacker intercepts it and swaps in their own key. When Bob later receives that key, everything still looks cryptographically valid. He can encrypt to it, he can verify signatures from it. The math works. The identity does not. This is the core trust problem PKI is designed to solve. Cryptography alone can protect data and prove that whoever holds the private key signed something, but it does not prove who that whoever actually is. We still need proof of key ownership that is bound to a real identity and is itself trustworthy. PKI fills this gap by introducing trusted third parties and certificates, which we'll build on next. Think of a digital certificate as an ID card for a public key. On its own, a public key is just a long number. You don't know who it really belongs to. A certificate fixes that by binding the public key to a specific identity, like a person, a server, or an organization. That binding is not based on trust alone. A certificate authority, or CA, verifies the identity, and then signs the certificate with its own private key. Anyone who trusts the CA can now check that signature and be confident that the public key inside the certificate really belongs to the named subject, and that it's only valid for a defined time period. This is the basic trick PKI uses. Instead of you having to know every server or person directly, you just need to trust a small set of CAs, and their signatures extend that trust to millions of certificates. By now, you've seen that a certificate is really just the visible tip of the iceberg. Public key infrastructure is the whole ecosystem that makes that certificate trustworthy. There are systems that issue and sign certificates, systems that validate the identity of whoever's requesting them, and directories that publish them, so others can find and verify them. There are also services whose only job is to say, this certificate is no longer safe, don't trust it. Around all of that, you have policies and procedures. Who is allowed to get which kind of certificate? How keys are protected? How long they're valid? And what happens during incidents? When all these pieces work together, technology, processes, and governance. You don't just have a file called a certificate. You have a managed lifecycle of digital trust that your applications and users can safely rely on. Traditional security worked like a castle and moat. If you were inside the network, you were assumed to be trusted. That model breaks as soon as an attacker gets inside, or when users' devices and apps are spread across cloud, home, and office. Zero Trust flips this completely. Nothing is implicitly trusted. Not a laptop, not a user, not even an internal service. Every access request must prove its identity and be re-verified continuously. PKI is what makes that proof possible at scale. Certificates give each device, user, and API a cryptographic identity that can't just be guessed or reused. When a connection is made, certificates are checked. Is this really the device it claims to be? Is this the right user? Is this the genuine service? Because these checks are based on strong cryptography and a trusted CA hierarchy, you can enforce never trust, always verify across thousands or millions of interactions, without relying on a fragile perimeter or on passwords alone. PKI isn't just a back-end security feature. It underpins almost everything you already do online. Every time you see HTTPS and that lock in your browser, PKI is authenticating the website and encrypting the traffic, so your credentials and payment data stay private. The same trust model scales out to billions of users globally. Inside enterprises, PKI is what lets laptops join Wi-Fi securely. Employees connect over VPN, encrypt their email, and let back-end services talk to each other safely through certificates and mutual TLS. It quietly enforces who are you, and are you allowed to be here, for users, devices, and APIs. Looking ahead, the same principles will secure huge fleets of IoT devices, enable passwordless logins based on strong cryptographic identity, and even help validate blockchain or other distributed transactions. So as we move into PKI strategy and architecture in the rest of this course, remember, we're not designing an abstract system. We're shaping the trust fabric that real people and critical systems already rely on every day. Digital trust starts with a simple problem. The internet by default doesn't know who to trust. Any machine can talk to any other machine, but identity is completely unproven unless we add something on top. We first tried to address this with shared secrets or symmetric cryptography. That works well for speed, but it breaks down at scale. If thousands or millions of systems need unique secrets, you can't manage or rotate them safely, and you still don't really know who is on the other side. Asymmetric cryptography fixes part of this. Key pairs let anyone verify messages from the holder of a private key. But a bare public key is just a long number. Without proof of who owns it, you still don't have identity, just math. Certificates close that gap. They bind a public key to a verified identity, and they're issued by a trusted authority. When everyone agrees to trust that authority, you can build large-scale, interoperable trust networks. Public key infrastructure is the complete system around those certificates. The authorities, the policies, tools, and the processes that keep them reliable. With that in place, modern models like Zero Trust can rely on strong, verifiable identities instead of weak assumptions. Today, PKI quietly underpins everything from web browsing and software updates to Wi-Fi, VPNs, and device authentication. Billions of people and trillions of transactions depend on it working correctly every day.